Sometimes you train a neural network and it feels like it's just memorizing the answers for a long, long time. It gets really good at the training data, but it's still surprisingly bad at anything new.
Yeah.
And then almost out of nowhere, it's like a switch flips.
hmm
Suddenly, it can generalize brilliantly. This weird phenomenon is called Grokking, right?
That's the one, Grokking.
And while it's fascinating, it also presents a real challenge for reliably training AI.
Absolutely. That delayed generalization, where a model sort of overfits the training data before it suddenly figures out the underlying patterns, well, it introduces a real element of unpredictability and inefficiency, too, into the training process.
Right, you're left wondering when or even if your model will actually learn to generalize properly.
Exactly. So the core question becomes, can we make this whole process more direct, more efficient?
Can we get models to generalize well without this frustrating and often really lengthy delay?
Yeah, essentially the real head scratcher is why this happens, and maybe more importantly for practical purposes, how we can skip this unpredictable waiting game.
And get straight to the good part.
Get straight to the good part. The model actually understanding what it's learned.
Okay, let's unpack this because that's exactly where this GrokTransfer idea comes in. This is a really interesting approach we've been diving into. And well, at its heart is a clever idea for speeding up this whole grokking business.
hmm
The core concept is basically leveraging knowledge from a weaker model that has already started to, figure things out a bit.
That's the gist of it.
We've been looking at a collection of notes on gradient descent analysis and also the research paper Let Me Grok for You, accelerating grokking via embedding transfer from a weaker model, trying to really get under the hood.
Yeah, good sources.
So our mission today is to understand the mechanics and, crucially, the innovations behind GrokTransfer. We want to look at its theoretical underpinnings and how it's actually shown empirically to boost how quickly neural networks can generalize.
Precisely. GrokTransfer is fundamentally a novel method designed specifically to accelerate that crocking phenomenon. And the central idea, the real insight, revolves around the crucial role of data embedding in determining the delay.
The embedding, how the data is represented.
Exactly, how the data is represented. The method itself has two key steps. First, you train a smaller, or maybe just limited in some way, weaker model on your target task.
Okay.
And you let it train until it achieves, some level of non-trivial performance on unseen data. It starts to grok, you could say, but it doesn't fully generalize yet.
So it's not perfect, but it's learned something.
Right. Think of this weaker model as kind of exploring the problem space, starting to identify some of the key patterns, but maybe not having the capacity to capture everything.
So this weaker model is like a scout then, going out and getting a rough lay of the land.
That's a good analogy, a scout, yeah. And the second step is where the innovation, the transfer part, really shines. You extract the learned input embedding from this partially trained weaker model.
Just the embedding layer.
The input embedding, yes. Then you use a linear mapping of this embedding to initialize the embedding layer of your target model, the stronger model you ultimately want to perform well.
Okay, so you're seeding the bigger model with the Scouts map, essentially.
Kind of, yeah. After this initialization, you just continue training the stronger target model as usual. But the crucial element here is transferring that initial understanding of the data's structure that the weaker model found.
Okay, here's where it gets really interesting for me. What's the thinking behind this? I would transferring the embedding from a model that hasn't even fully generalized help the bigger one generalize faster. What's the core insight, the innovation here?
Right, good question. The motivation stems from this observation that the way your data is represented, the embedding itself, profoundly influences whether generalization is delayed or if it happened more continuously.
How so?
Well, consider the modular addition task. You're adding two numbers, taking the result modulo some value. Basic arithmetic, but tricky for networks sometimes.
hmm
Experiments have shown that if you use embeddings that inherently capture some of the task's structure, like, say, Fourier embeddings,
Which capture periodic patterns.
exactly, or binary embeddings, which are naturally suited for numerical data represented as bits, if you use those, the model tends to generalize more smoothly during training. You see continuous progress, not that sudden jump.
Okay, so those embeddings have some built-in understanding or relevance to the task.
Precisely. They give the model a head start. Now, contrast that with using more general-purpose embeddings, like one-hot encodings, where each input is just a unique category.
No inherent structure related to addition there.
None at all. Or even using embeddings from a large language model like GPT, which are powerful but very general. In those cases, the training dynamics often exhibit that classic grokking behavior. Initial memorization, flat performance on test data, than a sudden jump in generalization.
Right.
The paper we looked at, Let Me Grok for You, actually has a really compelling figure too, illustrating this exact difference. Task-relevant embeddings lead to continuous generalization, while these general embeddings lead to the grokking pattern.
So the embedding layer seems key.
It strongly suggests the embedding layer is a key bottleneck causing the delay. And the innovation of GrokTransfer is that it cleverly creates a more task-relevant embedding for the stronger model, one learned by the weaker model, without forcing the stronger model to go through that initial lengthy memorization phase from scratch.
So the idea is that the weaker model, even though it can't fully solve the problem, still learns an embedding that's more useful, more task relevant than just starting with random initialization.
Precisely. It captures some essential structure. And to really nail this down, the researchers explored the theoretical underpinnings of GrokTransfer. They used a simplified, but mathematically tractable, scenario, a two-layer neural network trained on a high-dimensional XOR classification task.
XOR, okay, like a basic logic puzzle.
Kind of, yeah, but high-dimensional. Think of it like creating a basic puzzle where they could mathematically prove a key aspect of GrokTransfer works.
What did they prove?
In this theoretical setting, they showed that by using GrokTransfer, by initializing the stronger model with the embedding from the weaker one, the target model could indeed generalize directly, without that characteristic delay.
Wow, okay, so the theory backs it up in that specific case.
Yes, it highlights a significant theoretical advantage, showing it's not just a random empirical trick.
That's a pretty significant theoretical result, but how does this play out in a more concrete example? Can we see the mechanism at work?
Yeah, they illustrated this further with an XOR cluster data case study. It's a bit more complex. Imagine data points in a high-dimensional space. The actual label depends only on the product of the first two features, that's the signal.
And the rest?
The rest of the features are just random noise. So the network has to find that signal amidst a lot of noise.
Okay.
Now, a standard two-layer network trained on this kind of data shows clear grokking. It overfits the training data first, gets good accuracy there, but struggles on test data, and only much later starts to generalize.
Yeah, we've seen those kinds of training curves before, that frustrating plateau, then maybe a jump if you're lucky.
Exactly. Now, here's where GrokTransfer comes in. They train a much weaker model, one with only 3 neurons, on the same data.
Only 3, that's tiny.
Very small. And because of this limited capacity, the weaker model physically couldn't perfectly learn the task. It could only achieve around 75% test accuracy.
Okay.
However, crucially, it did manage to learn a subset of the relevant features. It started to pick up on the underlying structure related to those first two features, even if it couldn't fully express the solution.
So its limitations forced it to focus.
In a way, yes. This limitation in what the weaker model can represent is actually key. It forces it to find a compressed, useful representation, focusing on the most important aspects, even if it can't solve the whole puzzle. They formalize this idea in their Lemma 3.1, showing why this limited expressive power makes the weak model's embedding particularly valuable.
So it's like the weaker model learns to see some of the important pieces of the puzzle, even if it can't put them all together.
That's a great way to think about it. And when they then extracted the learned embedding from this weak model and transferred it to a stronger target model, well, something remarkable happened.
What?
Figure 5a in the paper shows how this transferred embedding creates a much better separated data representation. It maps the data into a lower dimensional space where the signal stands out more from the noise, a higher signal-to-noise ratio.
Oh, okay.
The essential information basically becomes clearer, more accessible for the target model right from the start. This improved representation is a core element of GrokTransfer's innovation.
That makes intuitive sense. If the data is presented in a more organized, less noisy way, it should be easier for the next model to learn the actual relationship.
Exactly. And their theoretical analysis of this target model, the one with the transferred embedding, well, under certain reasonable assumptions about the data, initialization, learning rate, model size, they call them A1 through A5.
Standard stuff for theoretical proofs.
Pretty standard assumptions, yes. This analysis culminated in their Theorem 3.2. And this is pretty striking.
What does the theorem say?
It demonstrates that with GrokTransfer, under these conditions, the target model overfits the training data and achieves near-perfect test accuracy after just one step of gradient descent.
One step, seriously.
One step, which is incredibly fast. And importantly, they argue this isn't just memorization. It indicates a feature learning regime. The model is quickly learning meaningful features from the data, not just acting like a sophisticated lookup table or kernel machine.
Wow. Compare that to the usual slow generalization.
Right. It's a stark contrast to the slow generalization seen in normal training on this task, which they show in Figure 4a. This near-instantaneous generalization in the theoretical setting really underscores the power of initializing with a good informative embedding.
One step to near perfect generalization. That's a massive acceleration. It really highlights the power of transferring that partially learned but more task relevant embedding.
It does. The initial memorization phase is essentially bypassed. That's a key innovation of GrokTransfer, skipping that whole slow start.
Okay, so the theory sounds really promising and it helps explain the mechanism. But what about, the real world? Does growth transfer actually work on more complex tasks, maybe with different types of neural networks?
That's the crucial next question, isn't it? And yes, the researchers conducted extensive empirical studies to check exactly that. They tested it on several algorithmic tasks known to exhibit grokking, things like modular addition, modular multiplication, and also sparse parity problems.
Okay, standard benchmarks for this sort of thing.
Exactly. And across the board for both standard fully connected neural networks, FNNs, and for transformers.
Ah, transformers too. Interesting.
Yes, GrokTransfer proved highly effective. It either eliminated or significantly reduced that delayed generalization. You can see this clearly in Figure 6 of the paper, which compares the training dynamics with and without GrokTransfer. The difference is often dramatic.
And it worked across different tasks, not just one specific setup.
Yes, across modular addition, multiplication, and parity. It's fascinating to see it working consistently.
And they didn't just stick to one type of model architecture for both the weak and the strong. They mixed and matched.
Well, they started with FNN to FNN transfers. They set up experiments for modular addition, multiplication, and a specific parity task called 40,3 parity.
Okay.
In all these FNN to FNN cases, they compared GrokTransfer with just training the target FNN from scratch. And the results were clear. The sharp phase transition, that hallmark of grokking, was almost entirely eliminated when using GrokTransfer. The generalization started much, much sooner.
That's pretty convincing for FNNs.
Definitely. They even did an ablation study, where they change one thing at a time to see its effect.
Mm.
They varied how long the weak FNN model was trained on the modular addition task before transferring its embedding.
What did that show?
It showed a clear positive correlation. The better the weak model performed after it had started to grok itself, so the more it had learned about the task structure, the better the transfer worked. The target model generalized faster and with less delay.
Ah, so the scout needs to have actually found something useful for the map to be helpful.
Precisely. That ablation study, shown in Figure 7, really underscores that point. It's not just any embedding from the weak model, it's the embedding learned after it starts understanding the task that provides the benefit.
Okay, that makes sense. But you mentioned transformers. That sounds like a bigger leap.
It was. And perhaps the most groundbreaking aspect of their empirical work was demonstrating this FNN to transformer transfer.
So training a simple FNN and then using its embedding to help a big transformer.
Exactly. They showed you can successfully transfer embeddings learned by a relatively simple, fully connected network to a much more powerful transformer architecture, one comparable in scale to GPT-2 small, so not a toy model.
And did it work?
Yes. Figure 8a in their paper clearly shows that this FNN to transformer transfer significantly accelerates the transformer's generalization on the modular addition task. It drastically reduces the grokking delay.
Wow. Transferring useful representational knowledge across such different architectures, that's pretty remarkable. That feels like a significant advance.
It really does. It suggests these learn embeddings capture something quite fundamental about the data structure that transcends the specific architecture, at least to some extent.
Were there any hitches, any challenges with that cross-architecture transfer?
They did mention encountering some training instability when using large learning rates in the transform initialized with GrokTransfer, so there might be some tuning required there, or maybe a further investigation into smoothing that process.
Okay, a practical consideration.
But the flip side is the computational cost. Look at Table 1 in the paper. It presents comparison. Because GrokTransfer lets the large transformer model bypass that long, compute-intensive memorization phase.
The phase where it's basically wasting cycles just memorizing.
Right. Because it skips most of that, the overall training time could be substantially faster, even when you factor in the initial time spent training the weaker FNN.
So you spend a little time training a small, cheap model, but you save a lot more time on the main, expensive, powerful model. That sounds like a very practical trade-off in many scenarios.
It's potentially a huge efficiency gain. That's a key practical advantage of GrokTransfer, especially for very large models where training time is a major bottleneck.
How does it compare to other methods trying to speed up grokking?
They did a comparison with one called GrokFast, which uses a different technique based on gradient amplification. They tested both on a two-layer transformer.
And
GrokTransfer showed a substantially smaller time gap. That's the difference in time between the model reaching, say, 95% accuracy on the training set versus reaching 95% on the test set.
so the gap between memorizing and generalizing was smaller with GrokTransfer.
Much smaller, yes. That's shown in Figure 8b. It suggests GrokTransfer provides superior acceleration, at least in that comparison, by directly addressing the representation issue via embedding transfer.
This all really seems to point back to the core innovation here, doesn't it? GrokTransfer isn't just some random trick. It's specifically leveraging the useful representational power that the weaker model develops during its initial grokking phase
Mm-hmm.
to give the stronger model a significant head start. It lets the stronger model effectively bypass that prolonged, painful period of just memorizing the training data before it starts to actually learn.
That's a perfect summary. That's exactly the idea. By transferring this informative embedding, you're essentially giving the stronger model a much better initial viewpoint, a better understanding of the data's underlying structure right from the get-go.
Allowing it to learn the true patterns much more quickly and efficiently.
Exactly. The innovation lies in recognizing that value in the partially learned representations from the weaker model and then exploiting it to bootstrap the learning process in a more powerful one.
Okay, let's bring this back to you, our listener. Let's try and summarize. So, what are the key takeaways from this deep dive into Grok transfer?
Okay, I think the main takeaway is that GrokTransfer offers a surprisingly simple yet quite principled approach to significantly speed up this whole grokking phenomenon in neural networks. By strategically transferring the learned input embedding from a weaker, partially trained model to a stronger target model, you can achieve much faster and more efficient training.
Less waiting, faster learning.
Pretty much. This method demonstrably reduces, or in some cases even eliminates, those frustrating generalization delays that often plague neural network training.
And we saw evidence for this both theoretically
Yes, in the XOR analysis.
and empirically across different tasks and even different kinds of models like FNNs and transformers.
Right. And the core innovation, the clever part, is really about using those partially learned representations, effectively taking what the scout learned to guide the stronger model towards quicker generalization.
And why should you, the listener, care about this? What's the bigger picture impact?
Well, because Grok transfer, or ideas like it, have the potential to make the training of large neural networks more predictable and, importantly, much more efficient.
Less guesswork, less wasted compute.
Exactly. Imagine being able to train powerful models without that uncertainty, without having to wait an indeterminate amount of time hoping they suddenly grok the task. This could have really significant practical implications for machine learning development.
Especially as models keep getting bigger and more complex.
Absolutely. The ability to accelerate this process and understanding the mechanisms behind it, particularly the role of these learned embeddings, feels like a notable step forward.
So the big question now, the one to maybe leave you thinking about, becomes, could the underlying principles here, this idea of leveraging partially learned representations from simpler models, be applied more broadly?
Interesting thought.
Could we extend this to other areas of transfer learning, or maybe use it in multi-stage training pipelines to further boost learning efficiency and generalization in even more complex AI systems?
It certainly opens up possibilities, doesn't it? Thinking about how learning in stages or transferring insights from simpler systems could be a general strategy.
Definitely gives you something to think about.